day, grade 12 chemistry students. Today what we're learning about is rates of reactions, okay? Over the next few lessons, a series of 3 lessons actually, we're going to learn about something called the collision theory. We're going to talk about factors such as temperature, surface area reactants, the nature of reactants, the addition of catalysts, then the concentration of solution control the rate of a chemical reaction. So what is a rate of a chemical reaction? Well, pretty much it is how fast the reaction actually occurs. The faster it happens, the reaction, the faster the rate is. The slower the reaction happens, the slower the rate. So let's explore some ideas about rate now. So why do reactions occur at all? Well, the answer is if you actually look at the particles, okay, or the molecules or atoms of a reaction, when they collide, the reaction will occur. And the more energy they collide with, the more likely it's going to occur. It's the equivalent of thinking about an accident, okay? Think about an accident being a reaction, okay? So in order to get a reaction to happen, your car has to be moving fast enough in order for the reaction to happen or the accident to happen. If it's moving too slowly, your car will just maybe, bounce off another car, cause you to get in trouble by your parents. But just a little scratch, maybe if you take some of your markers out and cover it up, your parents might not even know what happened. So you need enough speed in order for that reaction to happen. That's the first thing that we're going to decide. And reactions happen because of collisions. So what can we do to speed up the rates of reaction? Well, essentially what we have to do, guys, is we have to increase the number of collisions. And imagine you had a container here, and I don't know how this is going to turn out on the video, but you have lots of different particles in a container bouncing off each other. What can we do to increase the amount of collisions that happen? Well, one thing we could do is make them move faster. And what we would do is turn up the temperature and the molecules would move faster and they're more likely to react. So if we turn up the temperature, the speed will increase of the molecules and they're going to hit each other more frequently and more reactions are going to take place. Another thing we can do is increase the pressure, so we actually make our chamber smaller, and you'd notice it's hard to see in your video probably, but the reaction is more likely to occur because they're more likely to run into each other. Think of it as if you are in you're in a bouncy castle maybe with your friends, and you decrease the size of a bouncy castle, you're more likely to run into other people. If the bouncy castle is bigger, you're less likely to run into each other, you're less likely to have reactions. So we just learned that reactions happen because of collisions. Well, what can we do to actually increase the amount of collisions that take place? Well, we can control several things here. We can actually control the chemical nature of the reactants. For example, if we put something that's very reactive in a chamber, it's gonna, when it collides, it's more likely to react. If you want to think about the bouncy, no, so if you want to think about your car example again, it's like riding around with a stick of dynamite on the end of your car. If you're more likely to get into a little fender bender, it's more likely to explode. So similarly, if you are very reactive, if you collide with something, you're more likely to react. We can also, in the second example, we can also increase the concentration. So you increase the amount of things that run into each other, there's more likely to be collisions, more likely to be a reaction. Again, we've touched on this already, but if you increase the temperature, what you're going to do is you're going to increase how fast things are moving. They're more likely to hit each other more frequently, but also with a higher velocity. Temperature is kinetic energy, increasing kinetic energy, they move faster. So it turns out if you double the temperature in kelvins, you actually will double the rate of reaction, okay? The next thing that you can do is you can add something called a catalyst. Now, catalysts, what they do is they just help reactions along. They help the accident happen. They help the collisions happen and make sure that they're effective collisions, okay? So enzymes do this. They're examples of catalysts like amylase, lactase. They speed up the rates of reactions. And finally, surface area. If you increase the surface area in which the reactants can combine, you're more likely to have a reaction. So for example, guys, if you need to make a fire, if you just take a big piece of a log, you see the kids don't know this stuff, but if you take a log and you put it on a fire, it's not going to burn very well. If you chop it up into tiny, tiny little pieces, you increase the surface area in which it can react with oxygen, it's way more likely to react. So again, if you are a Boy Scout, you know first rule of making a fire is kindling. Cut up that wood, make it have higher surface area. So let's talk about how we can mathematically track rates of reaction. Well, the equation that we have is it's basically the rate of reaction is equal to the change in concentration over the change in time. So change in concentration, the final concentration right here, subtracting the initial concentration. And the change in time is the final time subtract the initial time. If you divide those two things, we can measure the rate of reaction. Now the units we'll get for this, for any rate, is going to be moles per liter divided by seconds, okay? Because time is going to be in seconds and concentration is going to be in moles per liter. Remember, guys, moles per liter is big M. So oftentimes they will show our units like this. So how could we measure the rate of reaction below? We have N2 plus O2 equals NO2. The first thing that we got to know is we got to balance our chemical reaction. So we put a 2 here, a 2 here. And we can measure the rate a couple different ways. We can monitor the change in N2 or O2, okay? Or, so, yeah, N2 or O2, or we can measure the rate of production of NO2. So N2 and O2 are going to decrease because they're reactants over time, and NO2 is going to increase. So I've just written this down. So the rate decreases in N2, change in time, or we can measure the increase of NO2, change in time. So really, we could also measure the change in O2. So let's take a look at an example here. It says the concentration of nitrogen gas decreased from 0.2 moles per liter to from 0.8 moles per liter to 0.2 moles per liter in 14 seconds. What is the rate? Let me show you how I would calculate that. The first thing that I would do is I would write down what is given and what I have here. So what I've done here is I've recorded my information. I have for N2, because it says nitrogen gas here, I'm just keeping track of that. It says my final concentration is 0.2 moles per liter. The big M means full moles per liter. And my initial concentration is 0.8 moles per liter. And my final time is 14 seconds, because it happened to be 14 seconds. And obviously my initial time is 0 seconds. So now all I do is I plug in my numbers and we solve our answer. Okay, so I've plugged my numbers in. We have 0.2 moles minus 0.8, 14 minus 0. The answer to that is negative 0.6 divided by 14 seconds. So therefore, our rate when we calculate it, it's going to be 0.043 moles per liter per second. Now, technically, guys, I think I have one significant digit here and two, so really it should just be 0.04 for doing significant digits. Let's just keep that in mind. Remember, M means moles per liter, and the S means seconds. Now, this is a negative value, actually. So that means the rate of disappearance. It's disappearing, okay? And the reason why it's disappearing is because it's a reactant, and reactants disappear, whereas products are produced over time. So reactants will always have a negative rate, while products always have a positive rate. So if we were going to actually graph our concentration in moles per liter versus the time that passes in seconds, if we were going to graph our reactants, we'd start with a lot of reactants initially. Then over time, what would happen is it would actually rapidly decrease initially, and then eventually it would sort of level out and until the point where reactants got to 0. So eventually the concentration of reactants would decrease almost all the way to 0. It would happen very quickly initially because there's lots of collisions, okay, initially. And see, because there's lots of collisions initially, the reaction happens very quickly. Now, if we look at reactants, the opposite thing is going to occur. Sorry, I'm going to change that. If I look at products, the opposite things are going to occur. Reactants decrease. Products, you'll see, will actually increase in concentration over time. So initially, you don't have any products at all being produced. Okay, initially when you start, it's just all reactants. But quickly, as the reaction happens, there's lots of collisions. But eventually, as the reactants run out, there will be no more new products being created. So eventually, the concentration will stabilize as well. So this is the blue line. It represents the products, and the red line represents the reactants. Now over here we say that this has a positive slope, and that's the products, okay? The negative slope represents what's happening to the reactants. So if I give you a graph like this, how would you even go about determining the rate? Think about it for a moment. Try and come up with a question. How would we figure out the rate from any point on this graph? What would you have to do? Remember, the rate's units are moles per liter per second. Well, what you would have to do is you would have to find the slope, okay? And normally when we're talking about rates, what we do is we take the rate and we determine at the beginning of the reaction due to the maximum amount of collisions. We want to know the maximum rates initially, okay? We don't want to know the rate at the end of the reaction. We want to know it initially. And so what we can do is we can find the average rate between 2 points, or we can find the instantaneous rate by finding a tangent. So let me show you what I mean. You should remember this from math. So to find the average rate, what you would have to do between these 2 points, let's say you want to measure it from, I'm just going to make up a timer, 2 seconds and 10 seconds. Well, what you'd have to do is you just draw a line between those and you find the slope, just like you would in grade 10 math, of that spot there. Now, if we wanted to find the rate just at a single point and not between 2 points, what you have to do is you'd have to draw a tangent and then find the slope of that tangent, and that would give you an instantaneous rate. Okay, so that would be instant rate, whereas the two lines, that would be an average. So a couple things that we should know, that if you have a tangent at any point, that gives you the rate of reaction at any instant. At any instant, sorry. The steeper the gradient, the faster the reaction. At the start of the reaction, the graph is always the steepest. The rate at the start of any reaction is always the fastest. As the reaction progresses, gradients always become gentler. The reaction slows down. And after some time, the graph levels off, and that signifies the end of the reaction. So there is two ways that we can represent the rate of reaction. Again, just to reiterate what we've been saying. You can measure the rate of the disappearance of the reactant because the reactant disappears, or you can measure the rate of appearance of the product. For example, let me show you how we can use these numbers, and it really comes down to balancing chemical equations. We balance this out, it will say 2, 4 here, and it's going to be balanced there. So it really has a 1 there, but we don't show it. Now this means for every 1 mole of O2 that's produced, okay, that means 4 moles of O2 are produced. So I'm just using the coefficients to determine the rate. So the rate is really related to how the coefficients that are in a balanced chemical reaction. We also can say, therefore, then, for every 1 mole of O2 being produced, that means that 2 moles of N2O5 are consumed. So the rate is relative to the coefficients that are in this balanced chemical equation. So let's take a look at this example here. It says that you have some ions. This is an iodate ion, this is iodide ion, and this is hydrogen ion. And it makes iodine, aqueous, and water. Now, it's a 1 to 5 to 6 to 3 to 3 ratio. It says, what are the rates of reactions with respect to the various reactants and products? The rate of reaction with respect to iodate ions, so it wants me, is determined to be experimentally 3 times 10 to the negative 5 moles per liter per second. This is what that unit is, moles per liter per second. And it's saying that that rate is located right here. So it's located right here, and it's actually negative. We consider it to be negative because it's saying that it's being consumed. So all these other rates are also going to be negative as well, okay, for the reactants. All the products are going to be produced, so they're going to have positive rates of reaction. Now, how do we determine these unknown ones here that I'm underlining? Well, I'm only going to show you one, and you should be able to do the other ones. But if you take a look, the rate with respect to iodate to iodide, this one with the 1 in front of it and the 5 in front of it, it's a 1 to 5 ratio. So really, guys, this is all we're going to use is the coefficients. It's almost going to be exactly like a molar Hopper stoichiometry type question. It's a 1 to 5 ratio. So we just have to multiply this number by 5. Let me show you how we set it up mathematically. So like I said, I'm just going to take my rate, but now I'm going to write down the type of chemical that's associated with that rate. Just like a molar hop here, we write iodate, okay, IO3, and we're going to multiply by a fraction. And we're going to use unit cancellations here, so I'm going to put IO3 negative on the bottom, and I want to go to iodide, so I put it on the top. So can anybody tell me what's the relationship between iodide and iodate? Well, the answer is it's a 5 to 1 ratio. So we just put our coefficients in here, 5 to 1, and then we cancel out our units. Do a little simple math. Now you can see our answer is going to just be this times this. I just took 3 and multiplied it by 5, which is 15. I changed the exponent. You can do that in your calculator. But the point is that the value up is going to be 5 times bigger than the value that I'm highlighting now. It's a 1 to 5 ratio. Knowing that, you can also just simply calculate it using similar steps to stoichiometry, the rates of every other single component in this balanced chemical equation. And the rates, according to this, the rates, the rates that I've highlighted here, the ratios are 1 to 5 to 6 to 3 to 3. It goes along with the balanced chemical equation. Okay, lastly, what we're going to talk about is ways to measure reaction rates. Well, what we do practically in the lab, guys, to measure rates, they relate to things. If things produce a gas, for example, you can measure the change in pressure, and that's related to the rate. You can also measure the voltage of a reaction, and that determines if more ions are being produced or being consumed. You can determine the rate. And finally, you can use something called colorimetry, which is the measuring of the intensity of a color. If a product is a certain color, okay, then it's going to increase intensity at a given rate, and therefore you can figure out the rate of reaction. If it's a reactant, it's actually going to decrease at a specific rate. And it's just, it will decrease in intensity in color. So before I leave you and watch The Walking Dead, what I want you to do is I want you to answer this question before you come to class tomorrow, okay? So you have a balanced chemical equation. You know the rate of consumption of each reactant. So I want to know what is the rate of reaction of each uh, reactant here, okay? So how is it being consumed? Okay, and if you know the rate of production of NH3, which is determined experimentally to be 4 times 10 to the negative 3 moles per liter per second. So find this rate here, find this rate here, and find this rate here. And it should be related to the coefficients. So that shouldn't be that difficult. I hope not anyways. So to summarize really quickly, how do you find the rate of reaction? Well, if you get equations on concentration and time, you can just do rate equals change in concentration over change in time. Now let's say the second thing that we learned is if we know the rate of one thing in a balanced chemical equation, we can just use the coefficients to find the rates of everything else. That's the end of the video. Enjoy your night and see you soon.